Wow, well, welcome back again. Looks like we're at start time. And we got started already in chapter 4. So I was kind of been saying this as the semester began. It's kind of our first goal here to get an understanding of these first 4 chapters. Where chapter 4 is really all the pieces put together. So these individual chapters, 1, 2, and 3, are now going to be put together here in chapter 4. So that's why I was encouraging you, and again encouraging you, get to chapter 4, start doing the homework in chapter 4. When's your first test?
2 weeks.
Yeah, it's 2 weeks, so you don't have to panic yet. But I'm just trying to give you a fair warning. So if it gets close to the time and you haven't studied, at least I can say I did my part of it and you didn't. But anyway, so hopefully that's not the case. Hopefully you're working in chapter 4 or getting started and thinking about chapter 4, because it would be really nice to dive into chapter 4 as soon as you can, and take advantage of particularly that Friday MC, because there really, even though there's 2 Fridays between now and the test, there's only 1 Friday MC, because we have the holiday coming up here, not this Friday, but the next Friday. Now Don will probably do an extra MC. I don't want to put any words in his mouth, but he'll probably do an extra one that Sunday before your exam, or that Monday. The Monday's a holiday too, so maybe he'll jump in onto that Monday. So we don't have class there too. So.
Wait, so it's Friday? It's a 4-day weekend, or what is it?
Yeah, the 4-day weekend for the school. In other words, the school will be closed Friday and then Monday. Not this weekend, but the next weekend. You know, the President's Day thing. Hope I'm not telling you the wrong thing. I better check. Yeah. So the Wednesday of that week will be the test. And that's kind of what I'm getting at here, and kind of my concern is that as we get into next week, we'll have class on Monday, we'll have class on Wednesday, but then I won't see you again until the day of the test. It's a whole week later. So the good thing is you got lots of time to do it. Maybe the bad thing is it's not time here, it's time on your own. So certainly don't think it's a holiday for you, it's a holiday for the school. You're going to be studying. Okay. And so that's the 4-day weekend coming up. All right. So anyways, 2 weeks away, and so now I just want to kind of dive right in here into chapter 4, pick up where we left off, and like I said, if these make sense to you, that's a good first step, and then if you can do them, that's a good second step, and so you're probably in a good position to do the test when you get that far. In fact, next week's lab is kind of a fun one. Hope you'll enjoy it. It really is a 2-dimensional one, very different than the labs we've done. This one is not done in any way with new technology and all the computers and all those great interfaces. This is just really just shoot a ball across the room. It's low tech and one of our best labs we have, so it's a nice one. All right, well, here's where we left off. I left off with this idea. If you know position, could you get velocity? If you know velocity, could you get acceleration? And I'm hoping the answer to that is yes. We went kind of quick there at the end, but I was trying to rush to make sure that was in front of you, and so that you would at least be pondering it and thinking about it, maybe not actually starting the homework problems, but we were trying to show, or I was trying to show you, that it's really the same idea. If you look at the rate of change of position, you get velocity. So this is that same little diagram that we saw in chapter 2. The only thing that's new is I've got a little vector symbol. So that's kind of what we've done for this last week. We've changed from a 1-dimensional motion to a 2-dimensional, and even going into 3-dimensional motion. Although, like I said, I don't think we'll see any 3-dimensional motion this chapter, or even in the next chapter, but definitely in chapter 6. And so here is this same idea, and so we're just going to take the derivative, except now we got a derivative of a vector, and as I was trying to show you last time, you can do a derivative of a vector. Maybe you haven't done it in your math class yet, but you saw how it was just broken down into 2 pieces, an x and a y. And so more on that again, but now here's the next piece. If you know the velocity, could you get the acceleration? Sure, the derivative of the velocity, with respect to time, I should say, is the acceleration. Sure. And then, of course, could we do the reverse? I didn't mention it last time, but we did do it in chapter 2. What's the reverse? How do I get from acceleration to velocity? Yeah, if you integrate acceleration with respect to time, you will get velocity. And could you get position from velocity? Sure. Integrate again. So the integral is the undoing or the antiderivative, right? It undoes the derivative there. And so that's the connection here. Should I shut this for the glare again? Hurry up. Perfect timing. We're just waiting for you. Now we can get started. Okay, so here, then I'll put a little box around it. This pen's kind of drying out here. But there's the box around it, and I'll joke again with you like I did on chapter 2, although it probably wasn't funny then. You want all the answers to all the homework problems? And I'll go one step further. If chapter 4 is the consolidation of all the other ones, do you want all the answers to all the homework problems for all these first 4 chapters? And since the test is on these first 4 chapters, do you want the answers to all the test questions? There it is, right there. Okay, that's it. All right, you're going to start right here and then put the details together. The details will vary. Sometimes you'll have a single object, sometimes you'll have multiple objects, sometimes they'll start from rest, sometimes they won't, sometimes they'll have a constant acceleration, sometimes they won't. And so you've got to put together the details of what happens, but it really fits, and be a good sales pitch time to grab the syllabus, cross the top. You're going to keep hearing this all semester, but you really want to make sure you understand what physics is about here and what the design of the world is all about. Physics is about knowing how to apply a few powerful fundamental concepts to explain a universe of physical phenomenon. And so when you get that idea, you will see, as I said, you don't really need or want a cheat. Well, maybe you'll still want a cheat sheet. But you're not going to need a cheat sheet because there it is. You can memorize that. There's nothing more you need to write down than that little step. And then the hard part begins. It's that deductive reasoning. It's read that problem and apply that to this problem, or to the next, or to the next, or to the next. And so we're going to do the same thing. I'm just going to go through example after example after example. I'll start with abstract examples, then I'll lead to examples in the book, and we're just going to see, could you follow that reasoning? Could you do the same thing? And at first, you know, we don't expect you to be able to do the same thing. But as I do more examples and as you do more reading and more lab, then yes, I do expect you to be able to do it on your own at some point. And 2 weeks will be your test to see, can you do it on your own? And so that's this whole idea. So let's work on problems. I'll start with some abstract ones like we did in chapter 2. If you remember chapter 2, kind of the first thing I said is, well, a lot of problems have a constant acceleration. They're kind of the easiest ones to work with. And so why don't we start there? And I'll say the same thing. Why don't we start with a constant acceleration? And so I'll put the condition, if A is a constant. Okay? Of course, now it's a vector. So what do you mean by a vector is a constant? Well, if you remember from Wednesday here, we worked out this idea that when we now talking about an acceleration, now that we're talking about two-dimensional motion, you're talking about how does it change its speed in the x direction and how does it change its speed in the y direction. And so there's 2 parts to this. This part here being how is the velocity in the x direction changing, and this part here being how does the velocity in the y direction change. And so again, we're just doing chapter 2 twice. I like it, right? Two-dimensional motion. One-dimensional comes two-dimension. I like the numbering, right? 2 twice is 4, right? So chapter 2 twice is chapter 4. Kind of sums it up really simple. That's what we're going to do. We're going to be doing one-dimensional motion twice. And this little mathematics that we learned in chapter 3 helps us do that. And so that's why we learned that new notation here. Watch. Remember what we did first in chapter 2? We said, okay, from acceleration, could you get velocity? Let's try it. Can you? All right, so you get velocity, vector, from the integration of the acceleration vector. All right, now using this condition that a is a constant, well, what would I have? Well, I guess I'd have an integral, and I'd have an ax I hat plus an ay j hat. And we're kind of back to the same conversation that we had at the end of last lecture, where I said, could you take a derivative of a vector? You've never done that before. But after kind of breaking it apart, you see, oh yeah, that's not any different. I would just be doing the rules of mathematics that I already know. And I would say the same thing. Have you ever done an integral of a vector? Well, technically no, but could you do it? I bet you could. Let's see it. This is our first example here. And so you see it right here that I take the vector and I break it down into the two pieces that it is, remembering that it is a constant. And so I should come back here. When you say the vector is a constant, what do you mean about these separate components? Yeah, they're constant separately, right? Because for this to have the same magnitude and the same direction, neither one of these can change. So make sure you catch that, because as I go to do this integral here, I am going to separate it into the two pieces that this integral is. One involving the x's and one involving the y's. And so the I hats and the j hats keep it separately. And I'll go through the work, but I'm hopefully you're noticing, wait a minute, isn't this the same integral we did in chapter 2? Except now we're doing it twice. Exactly. Watch what happens here. If I do this integral, what do I get? Well, as we did back in chapter 2, in this special case where a is a constant, I can pull the a out in front. What do I get then? Ax times t, right? Now I'll pause there. What else though? Plus constant. And you had a great lab this week that it's easy to forget that constant of integration. You make your little column, you know, you took the data for acceleration, you were supposed to find velocity and position from that, and of course what you did is you integrated and added a constant. And some of you forgot to add a constant at first, you know, and it gave me a chance to walk around and say, jokingly, well, how'd you get it? And I said, you said, oh, I integrated. I said, yeah, you integrated and added a constant. And you said, yeah, right, I did. And that's about the time I walked away and left you to think some more there, right? So don't forget you're going to add a constant. So let me call it C1. Now all of this, I haven't done anything with this I hat yet. Well, how would I treat this I hat in an integral? Right, well, like we did last time, it is a constant. So with a derivative, we know how to treat constants. So we did that, and then the same thing here. It's a constant. And it's not a constant like the number 5, but it means something. It's a constant like a unit, right? It's constant like it means I hat, right? 3 I hat means I plus I plus I. So it's the same way. So I'll tell you what, I'll group it together like this and put the I hat out there. How's that? Okay? And so this would be your first integral of a vector. But again, I want you to see, even though it's a vector, really all that means is you break it into the two pieces, you pull out the I hats and the j hats as constant, and now you're just integrating your functions. And so it's the same integrals that you did in your Math 150 class. It just got the two pieces. And then plus, I'll do the same thing over here. What do you think happens here? Yeah, and hopefully you're going to see it's exactly the same integral. So this is the same integral we got in one-dimensional motion. Now we're just going to get the same integral twice. And so this would be a yt, and maybe I should put constant number 2 here for a constant of integration there. And so I wanted to take this time to show you that I am doing what I did in chapter 2 twice. In fact, we didn't stop there. What did we do next, if you recall? We kind of stopped and said, all right, let's study this. The same thing you did in the lab this week. I said, now that you figured out there was a constant, now you had to pause and say, oh, ooh, well, how do I put that constant in? And I was like, well, okay, the first thing you have to do is ask yourself, well, what does it mean? What is the meaning behind that? And so we're back to that phrase here of when we get into applied math here, it's don't just do the math read the math. What does it mean to you? And we did the same thing in chapter 2. And if you remember, we paused and we looked at this. And since all this stuff is in front of the I hat, you might be thinking of this as the velocity in the x direction. And hopefully, all this stuff, you're thinking of it in terms of the y direction. That's what that means. And so if you study this closely here, you will look and you will see hopefully what that means. So what does constant C number 1 mean? Yeah, and so if you look at it, if you were to put time equals to 0, your velocity in the x direction would be that value, C1. So C1 must be the initial velocity. So let's change the symbol from C1 to Vx initial, something that will remind us. And so I like to cross this out and say, okay, this is Vx initial. And same logic applies to the y direction, because again, it's the same thing we did in chapter 2, just twice. And so I think I've said that a lot now, and that's my whole point. We're just doing one step up from chapter 2. We're putting chapter 2 together twice. But this would be initial velocity in the y direction. So here's what we have. We have the answer of the velocity vector. The velocity vector then becomes initial velocity in the x direction times acceleration in the x direction times time. And so there is the x component. And then we have the other term, which is the y component. And I'm changing the order of these terms here so that they will look like the same order that we had back in chapter 2. And so doesn't that look like just what we call the kinematics equation number 1? We saw it in chapter 2. We did the lab on it this week so that hopefully you would remember what it is. You did a whole homework assignment on. So I suspect you know that equation already and you know it well. And that's my point. It's the same equation, just now I'm going to put little subscripts x to represent that I'm talking about the x motion and subscripts y to say I'm talking about the y motion. And so equation 1 really becomes equation 1a and equation 1b, if you will. We've got those two parts. In fact, it might even be worth putting over here in a box and say, okay, we could have one equation, which is the velocity in the x direction is the initial velocity in the x direction plus acceleration times time. And this one here, velocity in the y direction, becomes initial velocity in the y direction times acceleration times time. And I'm going to put them in the same box so you still see them as that same one equation. Just one of them has x and one of them has y. So now as we look at something moving in 2 dimensions, we have to look at how is it moving in the x and how is it moving in the y. The total is the combination of the two. And so we go back to our vectors and we go from Cartesian coordinates into polar coordinates. Well, let me keep going with it. Oh, yeah.
Explain the integration between a sub x I hat down to
Here?
there.
Are they both constants, so they go outside?
Is what both constants? Right. So ax is a constant only because I said it was for this special case. Is it always a constant? No. But for this first case, it is. Okay, so this result is only valid for constant accelerations. Is I hat a constant? Yeah, and it's always a constant. So no matter what integral I'm doing, I can treat I hat as a constant because the meaning of I hat is one step in the x direction. So I can pull it out, although I did pull it backwards instead of forward. Okay, and so then I just have an integral of dt, and that with the a in front, right? So, well, good. So you see it, right? Okay. And so then if we look at what we did next is we said, okay, so we just did this step. I gave you the acceleration. We integrated it to get velocity. Could I get an equation for position? Well, sure, I would do what? I would integrate, again, I would integrate velocity. So let's try that one. So here's I would call check number 1. The x component, the y component. Maybe I should ask, I hope I haven't confused you. Do you see how this is the same as this? Here's written with the I hats and the j hats, so this is the x component, this is the y component. This is written separately at 2 separate equations, so I guess I'm kind of hoping they look the same to you, and I just dawned on me that they may not this early on in the use of vectors and the I-hats and the j-hats. But this has got to correspond to the x, and this has got to correspond to the y, which is, you know, what the I-hats and the j-hats mean. Okay, well, I'm going to continue on here because my second question, and it's really the same question we asked in chapter 2, is could you get position? Sure. Integrate again. All right, so that's what I'm going to do. I'm going to integrate again. So if I integrate the velocity vector with respect to time, that means I would have these two pieces. I would have initial velocity in the x direction plus acceleration times time, and then there's my I-hat, plus, and I guess it's an integral of the whole thing, so, but this is the x part of it. And then I would be integrating the second part also, the y, or the vertical motion of it. And so there's my integral. And I got to admit, at this point, this is where I was saying on Monday, it looks kind of scary. You walk into a class seeing that on the board, that's kind of long there. It's got all these symbols, it's got these subscripts, it's kind of long. But if you break it apart, I'm hoping you'll see, isn't it just the integral of the x plus the integral of the y? And isn't this the same integral we did in chapter 2? And so I'm going to do it for you, but I'm going to ask you, I bet you can tell me the answer before I even do it. Could you tell me the equation for x? Could you tell me the equation for y? I bet you could. Initial x, a velocity initial in the x direction times time plus 1/2 acceleration in the x direction times squared. Look familiar? Yeah, it's exactly the same equation because it's going to be exactly the same integral. The only thing is we're keeping x's with x's and y's with y's. So we've had the little subscript there. And so we've got an x subscript together with our initial subscript. So some of these have a double subscript. But doing it for the y, we're going to see the same thing. We're going to just have a subscript y. So we're going to have initial position in the y. We're going to have initial velocity in the y. We're going to have an acceleration in the y. And so I claim that when I do this integral, I'm going to end up with the same answer that I got before. Just twice. One for x and one for y. And when you begin to see that, you'll begin to see that, yeah, these aren't so bad. Okay? But they are a step up from chapter 2. When you did chapter 2, there were some details. And some of you even came and talked to me and said, yeah, you know, this chapter 2 got, you know, you made it look easy when you talked about it, but there's some hard stuff here. And I was like, yeah, you know, you got to keep track of the details. I mean, let's run through it. And you know, most of you said, oh yeah, that makes sense when you do it. And I was like, yeah, see, it's hard, but it was keeping track of the detail. When did the tortoise take off? One of them was, you know, the tortoise was racing the hare, and so, you know, when did that one take off? Or where was the car when the light turned yellow? That was a hard one, that yellow light one there in chapter 2, you know. But keep track of those details, and then it all works into it. So I think it's more about the difficulties of keeping track of the details. And so break it into little steps, and each little step is pretty easy. That joke I was telling you, could you run a marathon? Just one more step. I mean, really? How hard is that? One step. And then after you do that, well, take another. And take another. And 6, 7, 8 hours? Who knows? You might be done, right? And so that's the idea of this problem, is these problems can get pretty long, and there's a lot of details in them. But if you can kind of see the big picture and kind of break it down chunk by chunk by chunk, it's like a marathon. It is going to be overwhelming and tiring and take a lot of time. But you can get there. It's one little step at a time. That's really what it is. And so that's what this is. This looks big and long, but it really is the same steps we took in chapter 2 twice. So I hate to say it this way, but I guess it's twice as hard as the last chapter we did. All right, so however hard chapter 2 was for you, double it, and that's what chapter 4 is going to be, right? We're going to keep track of that. All right, so let's give this one a shot here. As I do this integral, I will come up with that same thing. And the same logic hopefully applies. This is the initial velocity in the x direction. Put it together with the dt, and I am going to get the initial velocity in the x direction times time from that term. And then doing the integral on this term with the I hat and the dt, this becomes the 1/2 ax t squared. Okay? Now, you may argue that, wait a minute, I did an integral here and I did an integral here. Each of these have an I hat in them. Okay, so this really should be buried inside of an I hat, right? This one and this one. And then you may say, well, doesn't this have a constant of integration? And this one have a constant of integration? Okay, same thing we said last chapter. Technically, you're right. And if you want to call this C1 and C2, or since we've already done a C1 and C2, maybe we call this a C3 and a C4. But why call them separate? I mean, what's going to happen if you have an unknown C3 and add it to an unknown C4? Yeah, it's just going to be one unknown. And if you want to call it C5, okay, I will. So this plus C3, this plus C4, I won't even bother to think about and just call it C5. Right? Right, and then let's do the same logic of don't leave it as some kind of constant where it's like, I don't know anything about it. Pause and look closely at the equation, and if you do that, you will see, well, this being the x component is really telling me that I would get just the C5 if t was 0 here and here. So this was really telling me the initial position. That's what that one is telling me. And so this boils down to then initial position plus initial velocity in the x direction plus 1/2 ax t squared I hat. So there's our first half of the problem. And that is the same logic we did in chapter 2. But it's certainly worth seeing it again, because I know, 2 weeks ago when you saw it, it's, new. And not too many people really comprehend the meaning of scientific material after their first exposure, which we know that. That's why I tell you, read it before you come to the lecture, read it after you leave the lecture. So you read it before, you come, you hear the material, then you go, you read it again, you try the homework, you do the lab, and hopefully by all those exposures you got a good understanding of it, and the test will go very well for you. Same thing for the second half here. If I do this integral, you can see there's a lot of pieces. I'm not sure why I put that parentheses in there. It doesn't look like that one's needed. But if I do that integral, and being the same integral I just did, and being the same integral I did in chapter 2, it hopefully won't surprise me what I get. The integral of this number with the dt becomes the initial velocity multiplied by time. And technically you might say plus constant C6, if you will. I'll hold off on that constant, because then as I do this integral, this is 1/2 ayt squared, and I guess you would say technically some other constant. However, by the time I've done those two integrals and got to constants, I can say, well, those two constants would be added together and they would just be some other constants that I don't know, but it's nice to think of it as just one unknown instead of two unknowns. And now once it becomes one unknown, then I can stop back and read it again like we just did here and say, well, what would this constant mean? And going through that same logic, this is what you would get when t is 0, because when t is 0, these two go away. So this must be the initial y position. And so this equation becomes just like that equation, except it has y's instead of x's. And so we've got the initial velocity and the, initial position, initial velocity times time, 1/2 at squared. And so there's my second term. And so like I said, it's worth going through that. It took a little bit of time, but I think well worth it to go through and do those integrals again. You saw it in chapter 2, yes, but we'll see it again. But it really emphasized not just doing it again, which I think is helpful, because those constants are kind of interesting to make sure you comprehend those. Because so far, our constants of integration have always come out to be the initial. They don't always do that. That's why I keep emphasizing. Don't forget to pause and study the equation to see what the constant means. Don't just assume it means the initial position. It may not, and it soon won't. But it has so far in the easiest cases we've done. There's a logic behind how you got that symbol, and stick to that logic. It'll help you not only now, but in the future. All right? But there's our two sets of equations that I was saying. Okay? And so there is our equation for position. This being the position of where it is on the x-axis, this being the equation for the position of where it is on the y-axis. And so again, this is one big long equation, but it's got two parts to it. It's got the x and the y, which is why over here, when I asked you to take a guess what you think I will get, I wrote them into two separate parts. I got an x component, I got a y component. So again, same second equation, we just have it twice, just like up here. Same first equation, we just have it twice. Well, maybe to save a little time,
It seems like you're multiplying the constant of integration by the vector.
I am.
Why?
Well, that's how the math worked. I mean, this is an integral, and then this whole thing is times the I hat, right?
Is our integral times the I hat?
Well, let me take this little one over here, right? This piece of it came from this, well, it came from that piece, right? All right, so this is an integral of Vx initial plus Ayt plus I hat dt. You good with that? Okay, now, following this through, this I hat means times this whole thing, right? So maybe it would be helpful if I just put the I hat out there. How's that? Just to kind of get it out of the way for a second. Because that's probably what you're used to doing, is bringing your constants out in front. Although for some reason we like our I hats in the back, so we like to pull them to the back of the integral instead of the front. But if it helps, I'll pull it out there. Now let me just leave it there for a moment. And then I'll do this first integral. This is the integral of Vxi dt, right? And then this is the second integral, Axt dt. But again, notice these integrals are done, and when you're all done with the integrals, you're multiplying everything by I hat. And so when I do this integral, I get Vxt plus a constant. When I do this integral, I get 1/2 Axt squared plus a constant. Put it together, and that's the constant C5 that I put there. But this whole thing is times the I hat. Which is why then, if this represents initial position, it represents initial x position, because it's I hat. And that's why I said, hey, if you look at this, this is going to give you initial position. Which one? X. Because it's multiplied by an I hat. Everything in here needs to be multiplied by I hat. Because everything in here represents where is the position on the x-axis. Now, which is also why I could not play this same game of putting the constant here together with the constant here. Could I put those constants together? No, because this one is times I hat. It's a different term than this one, j hat. But I put these two together to get that one. That was justified. I put these two together to get that one. That was justified. But in no way would I put this one together. That would be great. Then I would only have one unknown, huh? Darn. I don't have two unknowns, but it makes sense because it's two-dimensional motion. I should have two constants or two unknowns. I should have what is the initial position on the x and what is the initial position on the y. And I must admit, when we first, this first example, which is abstract, is probably the hardest one to see because I'm putting numbers in there. I think they're going to make more sense when we finally get to some numbers here. Let's put an object in there. Well, I'll keep going. Anybody remember what we did next in chapter 2?
final velocity?
Didn't we get equation number 3? Do you remember how we got it? And do you remember what it was? Maybe I'll start with what it was. Because could I put it right here? I probably could put it right here without doing any work, couldn't I? So let me see. Wasn't it the one that had velocity squared? And it had initial velocity squared? And it had a 2 and it had an acceleration, right? Want to look familiar? It would not. It would change it a little bit though. What is it going to look like here now? Yeah, instead of velocity squared, it's velocity in the x direction squared. Is going to equal initial velocity in the x direction squared plus 2 times acceleration in the x direction times, yeah, x minus x naught, right? So in other words, we have that same basic equation. We just have to put it in terms of the x positions, the x velocities, the x accelerations. And wouldn't I have the same equation again for the y? So here's our equation number 3. And so this is what it should come out to be after a little bit of algebra. And in the interest of time, I may skip the algebra and do this one so I can show you some other things there. But I would say that's equation number 3, except I now have it twice. So call it 3a and 3b, if you will. But do you remember how we got it? Do you remember how we got equation 3? This is kind of an important step, because this is going to make this chapter more interesting, I guess. And I guess when an instructor says more interesting, it means more harder, more options, more combinations, and more challenging to figure out the answer here. But this is important to see here. How did we get equation number 3? Do you remember? We didn't integrate this one. What do we do? Yeah, this is the one that I said some of you may or may not want to memorize this, because we could have problems like this. We have a race car that starts from rest. And it has an acceleration of 5 meters per second squared. And it finishes the race at 50 meters per second. Right? How far did it go? And the point here is I didn't tell you about time. But I gave you enough information that if you used equation number 1 for time, you could get time. Then take that time and put it into equation number 2 and get position. Fair enough? So equation number 3 was this. We solved this one for time and put it into there. That's where that equation came from. Okay? Now, let me not do it again here, but just to remind you, that's what I did. How do you think I'd get this equation then? Now, you say the same way, but you really mean solve this one for time, because we know information about the y motion, and put it into here, right? And that would give you that equation. So that's why we have those same 2 equations. But do you see something else that we could do here? We got something far more interesting here. Yeah.
So do you see how fast it's going at the end? Divided by 2. Oh, wait, we're out of time.
What's different now is, couldn't I solve this one for time and not just put it into here? Couldn't I put it into there? And not just put it into there, couldn't I put it into there? And see this one I solved for time and put it there? Couldn't instead I put it there? Now putting it back to there would be the same as this, so okay, I don't have to count that one. And I'm not done. Couldn't I solve this one for time and put it into there? Wow. So I would say we have really expanded the number of possible equations here from 1, and not to 2, but to 6. Shall we work them all out? No, let's not do that. Not that it's not important, but why don't we wait for the problem, read the problem, and see if we need it for that problem. But keep that option open. Remember now, we've got a lot more possibilities. And if I were to write out all 6 of these equations, and you think you got to memorize them, now you're really going to want a cheat sheet on the test. And you're going to miss the point that you don't want the little cheat sheet, or maybe you want it, I should say. You don't need the little cheat sheet, because you can just apply it for that case. So keep that in mind. Don't be surprised then, and this is the lab we do next week. This is why I think next week makes a good lab. That, and for other reasons, is what you end up doing is you fire this ball up on the table, and it lands down here on the ground, and you're supposed to predict where it is going to land. Now you know the speed it fires, because you're going to measure that earlier in the lab, and then you're going to measure this angle. How in the world are you going to figure out where this thing lands? Well, I'm thinking, boy, to figure out where it lands, I need to know things like, well, what's the acceleration in the x direction? What's the velocity? But more importantly, I need to know the time, right? And how am I going to get the time? And if you see it right here, don't I know it lands on the ground? And so you're going to be asked to do this in a lot of problems, including the lab next week. If you measure the height of the table, don't you know where it lands on the y-axis? I mean, you don't know where on the x, so it might land here, and it might land here, and it might land here. Who knows? But you know it lands on the floor. So if you measure this distance, we can then use this equation to solve for time. Now we can put it into here. So this is represented by this little red one here. We can put it into here and figure out where does it land in the x direction. And that's what we're going to do. So in other words, with two-dimensional motion can get more complicated, because remember that if you know something about the y motion, which we do in this example, we can use that to solve for time. And then when we have time, we can apply that into the x direction. So we can get valuable information about what's going on with the x motion from time, because time is not an x or y component. And so use that information. Use something you know about the y motion to see what happens in the x motion here. And so that's kind of my fair warning for you in this kind of beginning step here is, you know, what goes on here in this problem. So with all that said, that's why I would say that this chapter is harder than chapter 2. And in this case, there's 6 options. So we go from 1 equation to 6. So it's not just 2 times harder, it's 6 times harder, if you will. So be careful of your details. But that's a good illustration. So I'm only going to write down these 2, but remember, there's really 6 combinations there. Now, maybe fortunately for us, that's the only possibility that changes, because look at the 4th equation. The 4th equation, and again, how did we get it, if you remember from chapter 2? Yeah, that was one where we solved this equation for the acceleration and put it into this one. And that's all we can do in here too, right? Because when I solve this for acceleration in x, I can't put it here, right? This is acceleration y, so that's a separate one. So I can't put it here, and I can't put it in here. I can only put it here. So it's really the same substitution, and hence the same equation. And so probably it's not going to surprise you that I get x minus x naught is equal to initial velocity in the x times final velocity in the x divided by 2 multiplied by time. And so that is what we got back, and we call this kinematic equation number 4. We get the same thing. It's just now we have subscripts for the x's because we've got x's. And we could do the same thing for the y. We could solve this one here for the acceleration in the y and only put it here. That's the only place it'll work. It won't work here and it won't work here. So we would have a 4th equation a second time, just like we had here. And so we don't have as many combinations as before, and you know, as this one. This is the only one that gets a little more complicated because time doesn't have x and y components. It's a scalar. It's not a vector. And so I'll put a little box around it too, and say, okay, you know, here's kind of your choice. You decide how many of these equations you want to memorize. I suspect if back in chapter 2 you've memorized all 4 of them, then you're probably thinking I'll do all 4 again, because all you got to do is put the little subscript down in there. If you thought you're going to only do 2, then you're probably thinking the same 2, just that these 2 now become 4 because we got the little subscript. But I'm trying to help you here by saying, look, there's not a new equation here to memorize. These are the same equations. This is the same concept. I should point out, though, you would only use these equations if, yeah, remember we started this whole conversation right there, constant acceleration. So only use them in examples where you have constant acceleration. So they're a great set of equations, and they're used a lot, but very limited, which is why I would say that is not nearly as important as that. That is the answer to chapters 1 through 4 and test number 1 are all right there. Okay, just apply. So you see how I got those from this? That's what I did. So I just kind of worked through and looked at that particular problem. All right, well, let me keep going with my examples. That was, like I said, an abstract example, and I'll do another abstract, but maybe more specific abstract, because I want to build on this. So this is what I get for constant acceleration. If you remember in chapter 2, after we worked out these equations for constant acceleration, I said, well, what is probably the most common constant acceleration? Yeah, and that's gravity. What's the acceleration due to gravity? Okay, so I heard that 9.8 again, meters per second squared, good. I even heard a negative, good. But really in this chapter we want to say j hat, right? Because when we say the acceleration now, we're talking about 2 dimensions. And so when I come over here and I put on the board here, let's look at a projectile and say, here, let's launch something across the room. Let's have an abstract discussion on what we'll call projectile motion. The first question I might ask is, well, what is the acceleration vector? Toss something across the room. Fair enough, it's 2 dimensions. And so what's the acceleration vector? And you guys said it right. What is it? Okay, so it has a j hat and an I hat. And the j hat is the negative 9.8 meters per second squared. But the I hat is 0. Now usually we don't write the zeros, so don't be surprised if we just put a negative 9.8 meters per second squared j hat. Okay? But I want you to remember, no acceleration in the x direction. And that's important because everything we're going to do now needs to be thinking about what's going on in the x and what's going on in the y.
I just want to ask if it's a projectile, couldn't it have an acceleration in the x direction? Like it's, I don't know, a rocket or something.
Oh, okay, fair enough. He's asking if it's a rocket. And I would say, well, if it's a rocket, would it have an acceleration in the x direction? Yes, but then I wouldn't call it a projectile. Okay, so a projectile is technically defined this way. You let go of it, and the only thing is gravity. So a rocket is not a projectile, but it is a problem that we need to know how to do. And one of the examples I have is exactly what you said. One of my first examples is a projectile thing. And then the next example is one with a rocket on it. So to make sure you see, what are you going to do when there's a rocket? So it's semantics, I guess, is what I'm saying. If I say the word projectile, I mean this. Okay? You throw something, and you don't have to just throw it. It gets started somehow. Who knows? This could be gunpowder shooting a cannonball. A spring is what you're going to use in the lab. But how it gets started is not relevant. It's after it has gotten started and it's flying through the air without any other effect. No air friction, no rocket, no parachute. Then we call that. All right, so there's the semantics. This is the acceleration because one of the things you're going to ask yourselves right away, like we did in chapter 2, is do you have a constant acceleration problem? So the answer to a projectile is yes, and this is the number. And in fact, we use that number so much. Do you remember how we gave a symbol to this? Yeah, the symbol was G. Now remember, G does not have the negative in it. So I'm going to put the negative out in front here. G is just the 9.8 and the units. It's not the negative sign. So we're really saying the acceleration is a negative j hat here. Okay? But nonetheless, here would be my first question. Could I use these equations for that problem? Yeah, why? Constant acceleration. Right. And so you just have to ask yourself right away at the very beginning, is this a constant acceleration problem? If it is, go ahead and use these. If it's not, go back to here and do the integrals. Okay? So let me try one here. It's going to be very similar to the lab you do and a lot of the homework problems. It'll be something like this. We'll take an object and we'll give it a little push at some velocity v at some angle theta. So again, I won't put any numbers in yet, so kind of an abstract example here, but let's just say it's a pen again. Or here, I'll use the eraser. You can see it a little better. Here's the eraser, and so I'll start right here and say, okay, I'm going to give it a little push and let go of it. And so after I let go of it, this is the point where I let go of it, okay? So it's got some initial speed, v naught. Or maybe I should call it VI. Sorry, I'm old school. I think your book uses always VI, not V naught. Okay. Well, no, they did that a few times in the problems too. So, oh yeah, you were asking about it. It's like, you know, yeah. So V naught, V initial, kind of the same standard. But I'll use a VI to kind of match this one here. Okay, so there's the initial velocity. So I have an initial velocity, I have some angle theta. All right? Could you write out the equation for the velocity of this object? Well, I hope so. Because you already answered the first part. Is it a constant acceleration problem? Yeah. So couldn't I use these first equations? So I could. And I would say that I would have two parts to it. I would have a description in the x and a description in the y. I would look at that and say, okay, the velocity in the x direction is initial velocity in the x direction plus acceleration in the x direction times time. I'd start right there. Now, in this problem, what is the initial velocity in the x direction? Good. So I'm taking you back to chapter 3, right? Or maybe you're still working in chapter 3. But it was chapter 3 that allowed us to break this apart into its vectors. I'll change colors so you can see it. Here's really what you're saying. That is really made up of so much in the x direction and so much in the y direction, isn't it? And the x direction here is getting from the cosine. So cosine of theta would be v initial x divided by v initial. So as I solve this math and I put it here, this would be v initial cosine theta. Do you see that? And so there would be my first step. What is the velocity in the x direction? And that's why we looked at all those polar and rectangular coordinates things of chapter 3, because I knew this was coming right away in chapter 4. We need that. We need to know what is the velocity in the x direction. Remember, nature kept it separate x and y. Our math keeps it separate x and y. So if you start out a problem by giving me in polar coordinates, you got to change it back into rectangular coordinates. So the first step right there is to figure out what is the initial velocity in the x direction. What's the other term? Plus what's that one? Right there, right? 0. So what this is saying here is there would be my equation, and I don't want to put a solid line around it. I'm afraid if I put a solid around it, you would really think you can, it's another one to memorize here. But there would be the equation for the velocity in the x direction for a projectile. Worth memorizing? I'd say absolutely not. No way. I mean, do you see where I got it? I mean, I got it really from this one. So if you're memorizing this one, just take that one and apply it to that case, and there you have it. Okay? In fact, all the equations I'm about to get, I would say, don't memorize any of those. They come from these, which of course comes from these. But I think it's kind of worth memorizing a few of these, even though they come from there, so you don't derive it. But anything beyond this, it's not. It's work it out. Go through the details. Now, if we stand back and read the math, what is this saying about the projectile? What is it saying about the velocity in the x direction? Does it change with time? No. And that's what that equation is saying. This is some number. If I had put a number like, say, 5 and 37 degrees, so 5 times the cosine of 37 comes out to be a 4. This is saying the speed is 4. And it is saying it's always 4. And so when you take this eraser and you toss it, it moves across at 4 the whole time. Never changes how it's moving in the x direction. And that makes sense, because didn't we say the acceleration was only in the y? 0 acceleration in the x means don't change your speed, and that's what this says. So it matches. It's not a surprise, I hope. It's look, right back here. You are saying do not change your speed in the x direction, and so this is saying your speed in the x direction is a constant. Yes, good. Right? It's exactly what that math says to me as I read the equation. Sure. How about the other equation? Could you give me the equation for the velocity in the y direction? Well, yes, I think so. Let's see. Acceleration in the y times t. All right, so what is the initial velocity in the y direction? Good. You guys got the idea. It's initial velocity sine of theta. So you got to do a little trigonometry. We got to go from our polar coordinate system into our Cartesian coordinate system. Okay. Now I'll put that one on the board over here too. But sine of theta would then be initial velocity in the y divided by initial velocity. So move that to the other side and you get this. So this is the initial velocity in the y direction. Then it's plus the acceleration. Well, what's the acceleration? Yeah, that's that negative g we just talked about here. So, negative gt. And I guess I'll put a little box around that one too, but I'll make it a dotted line, trying to emphasize I wouldn't try to memorize this. I mean, you see what I got it? You see how I just applied the acceleration for that case? And knowing it was a constant acceleration, I could apply it to these equations, which is really nice because I already got those memorized. So I just apply it to that case. So this would be my equation for the velocity in the y direction. It kind of matches this one. Now, does this one change with time? No, definitely. Right? I mean, a plot of this one would look, I guess, something like this. If you were to plot velocity in the y direction as a function of time, what would it look like? Would it be a line? Would it be a parabola? Would it be a hyperbola, an ellipse, a circle? Yeah, it's a line, right? It's linear with time. Would it have a positive slope, negative slope? Negative slope. Would it have an intercept of 0? Would it go through the origin? Would it have a positive intercept, a negative intercept? I mean, what's it saying? Right, it's saying this. There it is. This is your intercept, the y-intercept right there. This is the slope. And I hope it kind of makes sense. Does this equation and this graph match what you just saw for that eraser? Now, forget that it moves horizontally because this equation is just vertically. Doesn't that eraser look like it starts with a positive velocity? Good. And it gets less and less and less and less. Good. And it goes all the way to the top and it stops. Good. And then it down, 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 and gets faster and faster negative. Good. It does match. And so that equation, that graph is showing me exactly what happened to that thing. Went up, came down. That's what that says. And hopefully that's what it says to you. Because that's a tough skill to get. It's this reading of math that, it's, like I said, it's that applied math. Did you have calculus? Oh, absolutely. And you may have done very well in calculus, or very poor in calculus. But that could switch very easily in this class. There's a lot of people who've done well in calculus and not so well in this class. Or well in this class and not so well in calculus. Hopefully you do well in both. But applying it is a big step and an understanding of what's going on here. And so that's what I'm trying to get you to see. I'm trying to get you to read it. Read it. It's sort of, I guess, that step when you were in kindergarten. You learned the alphabet. That was one step. But just because you know the alphabet, you can't read. You still need more to that. And even if you learn to read, you still can't really interpret a story. What's the meaning behind the story? What's the purpose of the story? I mean, that's something deeper still. And that's where we are with our math, you know? What does it mean a little bit deeper? Well, I'll keep going with this, because these are great equations, abstract. But could you give me the position of this object? Sure, and I would say let's do the same thing again here. Let's write out, you know, maybe separate it into two pieces again, since I've got two-dimensional motion. How is it moving on the x-axis? How is it moving on the y-axis? Same question, really. Could I use these equations? Yeah, because it's constant acceleration. So if I write out these equations for x, I guess I would start here with x equaling initial position plus the initial velocity in the x direction plus 1/2 times the acceleration times time, right? And so that's the general equation. Good only for constant acceleration, but that's what I have for a projectile. So I start right there. And now start filling it in. I've got x equal, and here's a choice I need to make. I haven't made it yet. What is the initial position? Well, right, initial position is in reference to some kind of coordinate system. And if you'll notice, I haven't put a coordinate system on here yet. Well, I guess I kind of have, because I put an x-axis and a y-axis, and I said that. But I haven't put the origin anywhere. Where do you want to put it? Yeah, and I think most of you are saying, well, why don't we put it right there where you launch it, you know? So you, right here is where you let it go. And that makes sense to me, too. So let me actually put it in red up here. But really what we've been doing is we've been calling this the x-axis already. We've been calling this the y-axis. We just weren't sure where we put the origin. And so now I'll draw it up here and say, okay, there's where I'm going to put my origin. Certainly the x and y components we defined back here, and I didn't even ask you about that, and I should have, because that is a common mistake that's easy to make. You start working on an equation, you may not realize you've already called this x-axis and this the y-axis. And if you don't realize that, you might come over here and then decide, hey, I'm going to make a decision different than I made over here. And so it's real important that, again, you're reading your equations. And over here, I have chosen x-axis as positive when I made this statement. I have chosen y going up as positive, right? Actually, I chose y going negative way back here. So as soon as I made that choice, I made the choice of down is negative, which is the traditional choice, so nobody questioned that. But I needed to stick to it, and I need to stick to it for the rest of the problem. And so since I made the choice as down negative here, it's that I have that freedom of choice. Okay, good, I chose it. But now I have to stick to it here, and I have to stick to it here. I can't change that choice later on. So back here, I did make the decisions about the directions of positive x and positive y. I didn't make the decision of where the origin is yet. And that's what I'm addressing now. Now I need to make that decision. And once I make it, stick to it. Don't change it partway through the problem. And I would agree that it seems to make the most sense. Your author does the same thing. Both the author of your textbook and the author in your lab book, they say, let's take the launch point as the origin. So if you do that, and here's the advantage of it, what do you see about x naught? It's 0, and that's why it's a wise choice. That term goes away here. So I'll even put a 0 there to emphasize that I am now choosing. But I must admit, there are some problems where maybe picking the origin where it lands can be an advantage, not where it gets launched. And then the disadvantage would be right here, would not be 0. But the advantage of it landing at 0 may be more important. So we'll make those decisions as we go along here. Now, this initial velocity in the x direction is the same conversation we had a few moments ago. So this would be initial velocity cosine theta there. We would multiply by time. And then this term would be the acceleration in the x direction. We had that conversation. What's it? 0. And so after a few steps, this more general equation reduces to this equation. Again, put a dotted line, trying to emphasize, look, nice equation. It works great for projectiles, but don't memorize it. You see, I just got it from here. I applied the specific acceleration to this particular case, and so that would be a mathematical description of what is the position of the object as a function of time. I can even make a plot. I mean, what does this look like? X as a function of time. Is it a line? Is it a parabola? Is it a circle? Is it a hyperbola? Okay, it's a line, positive slope, negative slope, intercept at the origin, right? So this is what it's saying, where this part is the slope. So again, let's see, does that equation in math seem to match what I have right here? I mean, here I am tossing it across the room. The fact that it goes up and back down is irrelevant in that equation. That equation is only for x. And so watching it move across the room, it just keeps going the same distance x in the same amount of time. Isn't that what constant slope means? So sure enough, that's what this has. This matches this, which matches what I said earlier. Don't change your speed. Something that doesn't change your speed has a constant speed and keeps gaining the same distance for each second. Perfect. They all fit together.
Now, the slope wouldn't be theta, it would be some other number, right?
Oh, the slope is this number times the cosine of theta. So the slope is all of this stuff in front, like a y equals mx plus b, and if you have a times d over c times x, then that, you know, whatever's in front is the slope. Yeah, so all the stuff in front is the slope. Yeah, so right, the slope is not theta. So in no way would I want to call that theta, even though it's being launched at theta. And again, that's where reading the math becomes important, because that could be real easy. You're looking at this picture, theta. Oh, well, there's a picture. Two pictures, they got to be the same theta, right? No. Right? So easy to develop. Okay, and then going into the y direction, again, you can kind of see this on the y-axis, that I would start off and write out the equation for constant acceleration, because I've already concluded that this is a constant acceleration, all right? And then I can start plugging in my numbers for this specific case. Yeah?
On the first picture you drew,
yeah?
can we have x and t instead of y and x? Like, what is that?
Can we have x and t?
Yeah, like position and time rather than y and x for the.
Well, could we? Yes. And isn't that what I have here? This is a plot of x position versus time?
Yeah, I'm just wondering why that's x and t and that's y and x.
Oh, because I'm looking at something very different. And that's my point. Be careful. This picture is showing me part of the problem. This picture is showing me also part of the problem. Neither one is showing me everything. And don't misinterpret that. That's why this angle here is not the same angle. This is the physical space. This is xy. This is what you would see if you took a camera and took a picture. You can say, okay, I'm going to take a picture of it, and you would actually see it going at some angle, 37 degrees per se. And you would see it launched that way, because this is a plot of xy. All right? This you wouldn't see with a camera. You would never see this. This is just what is its horizontal position as a function of time. How does its position changes? If it helps, maybe this is what you would see. If you were watching the shadow, let's say the sun was straight up above it, and you were to toss this thing, the shadow would not show the up and down. The shadow would only show the movement in the x direction. So if I were to toss this across the room, and don't look at it, but look at the shadow, and take a video of the shadow. This would represent the shadow on the ground. And so that's something very different than what this is showing me. So that's why this is x and y, but this is x and t.
So if you found like the initial like over here, can you plug it into the equations over there?
Initial what?
Like velocity or whatever.
Well, in this example, I'm saying you're probably going to be given the initial velocity.
I mean, like if you find some kind of like variable
Yeah.
in these equations, can you put it in those?
Yes, yes, because these are still part of the same problem. So, yeah, I think what you're... and I kind of did here. For an example, what was given in the problem was initial and theta. What I needed was initial in the x. That was not given. So I had to take stuff from over here to figure out what initial in the x is and put it into here. In fact, what you're asking is a really good question because the lab is going to do this to you. The lab is going to say, find the initial speed of your cannon. And so you're going to fire it the first time at some known angle and see where it lands. And what you won't know when you fire it is how much time did it take to land and what speed did it fire at. Although on the vertical motion you'll figure out how much time. You'll put it into here to get what the initial speed is that you fired it. Once you get the initial speed, now you can come back here and change the angle and launch it at a different angle but a known speed. So I'm probably getting ahead, but what's nice about the lab is the lab makes you go both directions. They give you, the first part, they give you where it lands and you got to figure out what the speed it was fired at. Now you change the angle, but the cannon still fires at the same speed, so you use the known speed to find out where it's going to land with the new angle. And the lab's kind of fun because then you calculate where is it going to land, and then you fire it. And if it lands where you calculated, you feel good. If it's even close to where you calculated, you feel good. If it's not close, you're back. What did I do wrong? And oftentimes it's a sign error or just a math error. A few times it's just a fat finger calculator error type thing. But most of the time it's a sign error. Yeah. Yeah. Well, again, I'm being abstract because I think this is a good place to start. But they get more concrete as we get into some actual numbers. But you asked a good question. I'm going to play on that because I'm going to do another graph here and plot y versus time. See, and what does that tell me? See, that tells me different information than this one, which tells me different information from this one. And so each plot, each diagram, you got to be careful. What is it saying to me? Well, I guess I got to get the equation first. So let's plot this, but we got to get the equation. So same thing. Here is the y. What is the initial position? Yeah, we kind of made that choice already. We put the origin right where it's launched. So where does the initial position? 0. What is the initial velocity in the y direction? Yeah, that's what we did back here 15, 20 minutes ago here, right? So this would be initial velocity sine theta multiplied by t. What's the acceleration in the y direction? Yeah, that's what we did way at the beginning where we asked, it's a projectile, what's the acceleration? We said it was a negative g. So this would come out to be a negative 1/2 g squared. And so if I just get rid of the 0 here, I have this term, and I have that term. And so now I have equation for its position. But I'll say it again, equation worth memorizing? No, 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 no. A lot of equations, they came from here. And so you just got to look at the equation, I mean the problem and ask, are they asking me for velocities of it? Are they asking me for positions of it? What are they asking? And trust me, they won't ask for everything. So don't, solve for everything. You won't have enough time on the test. Now, if it's homework, you can solve for everything and then realize, oh, this is the only piece I needed. Well, that's fine. If you got an extra 2 hours, feel free to do that. But you do want to pay attention to what they're being asked for. And I got to admit, especially when you're a beginning student, it's like a puzzle. You don't always go in the right direction. If you do a maze, you got to figure out. The best part about doing a maze is actually just start the maze and find out what doesn't work. Because once you know what doesn't work, you kind of backtrack and go, okay, how come that didn't work? What options did I have in there? I'll go that way. Oh, well, that doesn't work either. Okay, good. And, again, and it's all these, you try it and you try it. And I'm afraid too many students think, well, I'm just not getting it. I tried it. Really? You tried it one time? Oh, 5 times. Oh, forgive me. No, it's going to take a lot more than that, okay? Especially some of these harder ones. That's the learning process. Find out what doesn't work and why it didn't work. And not only will you be able to get that problem, but you'll be well equipped for the next problem. And you'll find out that as you do more of these problems, the first one takes you a long time, less time, less time, less time, and hopefully then you've narrowed it down to, I can do those lickety-split, so on the test, that's where you want to be. You don't want to be taking 2 hours on one problem by the time we get to the test. You don't know it well enough to survive the test. You'll get one problem completely right, good. And the other 4? Nothing. That's not going to be a good score. So you gotta be doing them proficiently. Okay, and so it's do them, yes, and then do them proficiently. Well, anyways, let's look at this plot. What does this plot look like? Is it a line? Is it a parabola? Okay, it's parabola. You see that? Is it concave up, concave down? Okay, the peak of it, the vertex, where is that? All right. So it definitely starts here, fair enough? Time equals to 0, position 0, concave down, goes something like that. All right? So that's what that one is telling me. So again, make sure you read this graph carefully here. I mean, part of this is just doing these equations, but part of it is getting you, hey, this is an applied math subject, right? And it's probably the most advanced applied math subject you have had. I doubt if you've had any class that requires calculus, other than calculus itself, right? And so I'm asking you to apply your calculus and to read your algebra and to look at these. And so, I completely understand that the skill is new to a lot of you. I don't doubt that. So that's why I keep going this. And so forgive me those of you who've already got the skill and I'm boring you here. But read this. I mean, what is that thing saying to me? How would I interpret that? See, that's just the y motion, isn't it? And if I come back to your question, what does this one picture mean? What does this picture mean? What does this picture mean? I said this picture, this is the physical picture, right? This is what you would actually see as somebody tossed it. This is how it moves in the x direction. So this would be the shadow moving on the ground. What would this be? You're right, just straight up and down. If you were to stand on the side of it, right, and look at it as it's projected onto a wall. Let's say I have a block wall over there and I can make marks. What I would see is I would see the object go up and then come back down. It would be nothing more than if I had tossed it straight up and straight down. That's what it's showing me. It is not showing me a single thing about what it happens in terms of how it moved on the x-axis. This is showing me how it moved on the x-axis. This is just showing me how it moved up and then down. So this goes up to a maximum and then back down, and this is shown then below the ground or below whatever it's launched at. So if it's launched here, it goes up, but it comes back down, right? So again, just make sure we kind of interpret. Right, so like in the lab, this is going to start at the table, and if you call the table the origin, this is going to go up, and this right here will be the height of the table. But now this part is where it goes, so it's going to land down here. And so these are, yeah, coupled together, which, like I said, was what makes them challenging problems and interesting problems as the time couples together. In fact, maybe we should ask this question. Now that we've kind of studied this in great detail, maybe we can answer a question that sounded like a lot of you already knew the answer to. So I'll ask it again. It's not the answer. It's how'd you get the answer. If I toss this across the room, what shape does it have? Parabola. Parabola. Why? Why would you say that? What proof do you have that you would tell me that that is the shape of a parabola? Does this tell me it's a parabola? No. This is a plot of y versus time. What do I need for a parabola? Y versus x. I mean, yes, this is a parabola shape. I know that from this square. But this is not telling me it moves across space like a parabola. This is telling me it goes up and comes down. That's all that one tells me. If I wanted to argue that this is a parabola, what graph do I need to show that one? That's the graph I need. The function I need is what is the position of the object as a function of x. That's not what I have here. I have what is the position as a function of time. Here I have position as a function of time. Now I could put them together. If this was a math class, I'd call it a parametric plot, right? I'd solve x for time and put it into there. And that's what I'm plotting. And so what does the parametric plot look like? Well, I guess you already know. It's parabola. But that's your proof. Your proof is how does it change in space? How does the y change with x? That's the shape of it, not how does y change with time. So careful as you read this, because this is not telling you that the motion of it is a parabola. Now the shape of that is a parabola, but that's not what that's telling me. So to get this one, what am I going to do? Yeah, solve for time, put it into there, right? It's kind of that red little line I was talking about back here. Couldn't I do that? No, I guess it's not the red. Yeah, I guess it is a red one. I'm going to solve this one for time here and put it into there. So I'll give it a try. I'll start here by solving this for time. So time is, all right, and then I've got initial velocity cosine theta divided, no, sorry, the other way around. It's x divided by initial velocity cosine theta, right? I'm solving this one right here. Called equation 1 here. And I'm solving it for time. And now I'm going to put it into here. So y equals initial velocity sine theta, right here, multiplied by time. Well, time is x over initial velocity cosine theta. And then I've got the other term, which is plus 1/2 g. And this will be my x squared over my initial velocity squared cosine squared theta. Okay? And fortunately it simplifies a little bit. Initial velocities cancel off and I get a tangent of theta times x minus, I guess I just have a g up there, and then a 2, then the initial velocity squared, and then the cosine squared, x squared. And I'll leave the cosine down squared. You can call it cosecant if you want, or secant and move it up if you want, but that's not what I'm after. Well, here is 1/2 times g, so that's a g over 2. G over 2. And then a v squared down to the cosine squared. That help?
No, because I saw the x squared.
Yeah, now the x squared I put off to the side, only so that I can have you see how is y a function of x. What shape is this? How do I know it's a parabola? There's a square. Concave up, concave down. Down, right? Negative. Curvature here. All right, so a plot of this does give me a parabola, right? Something like that. So there's our proof. What shape does this have when it goes across the room? Parabola. There it is. I just proved it. So I'll say it again. This is not the proof for it's a parabola. This is. Okay? But like I said, good examples, abstract examples, and that's really my goal here for today. We'll get into numbers next week, but you know, this is good abstract examples. Yeah.
Never mind.
Okay. But now I'll pause. Didn't everything come from this? So I did this, which led to special details of that particular case. I thought I saw, no question, yeah?
Yeah, is there a certain theta where you could maximize the distance of your object?
Oh, I'm so glad you asked a question about that and other things. I mean, couldn't we ask a lot more questions? I mean, your question is, what would be its maximum distance? How much time is it in the air? What is its highest point? How far has it moved on the x direction as its highest point? How much time did it take to get to its highest point? How much time did it spend in the air? Shall we answer all those? We have the answers right here. And so let me clear the board a little bit, but I'll leave these basic equations here, the ones with the little box around them. Maybe I'll start here. And your question is good, but let me hold off on it. Let me just ask a different one here. Let me ask you this and say, all right, what is the height? What is the highest point this has? How am I going to get the highest point? Good. A lot of you see it right away here. There's something physical. This is the physics part of it. What is physically happening at its highest point? Does it stop? Okay, so it stops going up. So what does that mean? The velocity in its y direction is equal to 0. In the x direction, is it 0? No. All right, so there's always that first step. Interpretation of the question. You've got a description. Somebody's asking you something. Somebody's solving it. But take that and apply it to what does that mean here. And in this case, what it is saying here, and it has to do with air velocity, is this one won't change. But that's good because we already said this is a constant, so it better not. We better not be looking for where this is 0. That's never going to happen. But this one does equal 0, right? That was our discussion earlier. And so this one will tell me the time it takes to get to its highest point. It doesn't tell me how high it gets, but that was one of the questions I said. One of the things I'd like to know is how much time does it take to get. But if I were to get the time it takes to get to its highest point, what could I do with that? Then I could put it over into here, which tells me the height at that time. See the two-step process? All right. Now I got to admit, this would be a much easier problem if they said, give me the time when the velocity in the y direction is 0. It's plug and chug, right? Put in y equal to 0, solve for time. Easy problem. You won't see any of those like this, and not at this level. It misses the whole physical point here. Well, maybe a few, but you know, not many. And it's not just a plug and chug type of problems. I don't know if I said it to this class yet, but if you do that, you'll get half the problems and not the other half. You'll do okay. You'll get an okay grade. You'll transfer to an okay school. You'll have an okay career, right? And you got to do more than plug and chug. There's the depth of what's going on. What are the details in here? And why do we do what we do? That opens the door to creativity, to do the kind of things that have never been done before, to discover the something new, to build a new product, to do something that you say, oh, I'm going to look it up in a book. No, not if it hasn't been done before. You're not going to look it up. Okay? You're going to put pieces of knowledge together. If it's already been done before, you're too late. Sorry. You guys can't invent the telephone. It's been invented. Okay? It's done. Now you can improve on the telephone. You can improve on the computer. There's a lot of things still to be done, right? And as I said before, I'm still hoping for that microwave cooler there. I just need 2 of them above my stove. One for my chicken, one for my water. Ding, hot chicken, cold water. I got the chicken one. I need the water one, okay? What is that? Okay? And so there's all kinds of things. Or it's the new material that's going to build the bridge, stronger, lighter, the new airplane, stronger, lighter, so I can travel the world when I retire, and you can make billions of dollars and pay taxes and, you know, keep the country running, you know. That's this big picture in here. And so that's how society runs. All right, well, I'm getting off track here. Let's go back to the specific problem. That's the key, right? You've got to interpret. You've got to make an interpretation. What do they really want? So when the question asks the height at its highest point, you got to realize something about the physics. And you did. That the velocity would be 0. So if I come over here and do that calculation, let's see what I get. I'll give myself a little more room here. I don't think we'll need this anymore. But if I come over here now and take that equation which says initial or velocity equals initial velocity sine theta minus gt, and I set that equal to 0, there's the physical step there. There's the interpretation. When does velocity equal 0? And now I can solve the mathematics here. And again, we've got some abstract numbers, so when I move this over to here, I got my gt, I've got this, I've got t equals v naught sine theta equals to g. And so maybe I'll put a little circle around it. Again, a great equation. It tells me the time when it gets to its highest point. Going to memorize it? No. Work it out. Because how many times are they going to ask that question? Once? Something you could work out from there. And you see how simple it was, right? You're just going to put it into that problem, which came from this. So there's the time it gets to its highest point. Now I'm not done with the problem, but that could have been the problem. How much time did it take to its highest point? This was a two-step process because I'm asking what is its highest point? What is its maximum point? So I'm going to take that and put it into that equation. So that equation says y equals initial velocity sine theta multiplied by time plus 1/2 gt squared, right? And so now I can put in the value of time. The time where the velocity gets to 0 is at its highest point. So I'll put that in. So this is initial velocity times sine over g. So there's the time factor minus 1/2 g, and then I will put the time factor. So this is initial, this is sine theta, this is gt squared. And then to simplify if it can, and fortunately it can, it may not look like it right away, but these are like terms. This is an initial velocity squared and a sine squared theta over g. This has a negative and it has a 1/2 in front, but other than that, it's an initial velocity squared and a sine squared from here. There's a g upstairs and 2 of them downstairs, so leaving just 1 downstairs. And so aren't they like terms? Okay, so we can combine those together. And so this is a 1 minus 1/2, which leaves then a plus 1/2 initial velocity squared sine theta squared over g. And so there's a great equation that tells me, hey, what is its maximum height? Worth memorizing? No, no. But again, it's worth using and working out if that's the problem. In fact, it can, you know, be added to, because you asked the question about how far does it total goes. This would be about half of it if it was level ground. So maybe I should wane on that here. But here's the equation of how high it is. Yeah. Well, this is a 1 times that minus 1/2. So 1 minus 1/2. Yeah. 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 Slow me down if I do my math too quickly here, but that's part of my evil strategy. Just kind of push you a little bit more here, and the more we can do our math, the more we can stay focused more on the physics. But doing algebra quickly is, you know, a skill that develops, you know, with time, and you don't want to do it too quickly to make mistakes. So I don't want to do too quickly. Huh?
That's the height, right?
So this would be the height, and I don't know, so I'll put a little circle around this. So this is the time it takes to get to its maximum height. This is the distance or the vertical height it is. How far on the x-axis would it be? Can we do that one too? Sure, it would be this equation over here though, right? And so we could say how, if we're watching it, where would you have to stand to be right under its highest point? How far from the thrower, kicker, whatever this object is. And so then you're asking about the x position. So the x would be initial velocity cosine theta multiplied by time. Well, the time to get to its highest point is what we did back here. So that would be initial velocity sine theta over g, and so it'd be initial velocity squared cosine theta sine theta over g. So I don't know, maybe I'll put a circle around that one. But again, I'm not going to try to memorize this in any way, but I am going to say that may be the problem. The problem may be, okay, if there is a football player who then punts the ball or kicks the ball here, and somebody is standing right here, how far away do they stand when the football is at its highest point, and how high is the football? Right? That's what that's just answered, right? How far away is the kicker? How high is the football? How much time did it take for the football to get there? Okay? And so those are your different questions you could ask. Now your question was a little different. It was about landing again, right? So let me land it. Let's say this is a football. Let me ask you this. Where would it land? So somebody's punting a football. Where does it land? How far away? You might call this the range, is what your author said. What is the range of this? How far is this? 60 yards? 80 yards? Where does the ball land? Could you solve for that? So what do you know? What do you know about that problem? How would you solve that one? Where does it land? Yeah, and then the key to the interpretation here is right there. You know something about when it lands. You don't know its x position. You don't know how much time. But you do know its y position when it lands. If it's a football field. If it's a level ground. And this is different than the example I've been using about the ball being launched from the table. When the ball gets launched from the table, does it land at height 0? No, it lands, it looks like -1 meter, right? But a football, if you know anything about football, it is a level field and it lands at the same height it starts. So if that's the condition, if the condition is we start on the ground, we kick it in the air, and it lands on the ground, final position is 0. And that's going to be that first key step, the interpretation. What does that information give me? You describe the problem to me. What does it give me? Does it give me initial velocity? Does it give me final velocity? What does it give me? And in this case, it gives me final y position. So let's use that. If I were to use this equation and set it equal to 0, that's really what you're saying, right? V naught sine theta t minus 1/2 gt squared. Solve for t. Fortunately, it factors, so I don't have to use the quadratic formula here. And there it factors. And when it factors equals to 0, it gives two options. One option is t equals to 0. The other option is v naught sine theta minus 1/2 gt equals 0. Which one do I want? This one or this one? Yeah, it's this one here. Do I want this one? No, but what does it mean? Yeah, it had 0 when I kicked it off. Right, here's a football, I kicked it off. Did it have height of 0? Yes. It had height of 0 at time equal to 0. Makes complete sense. Doesn't surprise me it's an answer to the math. It should be. Now, it's not the one I'm interested in, so okay, great answer. So what? Move on. All right, this is the one I want. This is the time where it lands. All right, so I'll keep solving this for time. And so I got v naught sine theta 1/2 gt. Bring the 2 over to here, 2 v naught sine theta divided by g equals t. Now I did a lot of math there. Is that okay? Move things around. And so that is telling me the time of when it lands. Now look carefully at it and compare it to the one we did over here. What was the time it took to get to its highest point? Half as much, right? So you probably are thinking, why didn't I just take this and double it? And that would have been fine. But I didn't want to do that because I want you to see it does work out. It is a parabola, and the time it takes here to get to the top is the same time it takes to get down. At least if it's on the same field. When you do the lab, don't think that, because the lab, it goes down here. So the time it goes lower is more time than it took to get up there. So that's different. Or if it was landing on the roof of a building, the times wouldn't be the same. But in this case, it lands at the same height we kick it, and so the time to go all the way is twice the time for halfway. Well, that makes sense, right? Yeah.
As far as problem solving, when we have like real numbers, is it easier to use variables to find what you're looking for first and then plug in the variables?
I wish I could give you one answer to that. It's a great question. And it depends on the problem and depends on the individual on how they understand their math and work with their math. Complicated problems in general, I would say putting the numbers in people feel more comfortable with, and they get a number and they work with a number from there, right? If it's a two-step process, usually putting in the numbers now and getting time before you move on to the next part is better than the symbols. But in this case, I like to do the symbols so that I can kind of read what's going on at each step. So some people will say, you know, the symbols are better all the way through. And I would say they're better in the sense that they give you the ability to understand the problem better. And at some point in your life, I would expect you to be able to do that like I'm doing it, but not right away, you know. And so if you want to substitute your numbers and then carry a number instead of carry a symbol, that's, you know, that's good first step here in our first semester together. That'll begin to change next semester. You'll see next semester there's a lot of problems this semester where they give you the numbers. Next semester there's a lot of problems where they just give you the symbols and say solve it in terms of symbols. So you'll see that transition as we go for these next 3 semesters together. Okay, well, I'm not done with this problem. This is just the time it takes to land. My question, and your question really was, where does it land? What is its range? How are you going to get that? We're back to here, right? This is the one that says, give me the x position as a function of time. So I will take this time and put it into here, sort of like we did back here. All right, so let me do that. So I will put x. I will even put here range. And kind of give it a special name, because where does it land on a level field? Kind of limited, though, because it's only on a level field. And like I said, I keep emphasizing that level field, because I find students when they get in the lab next week, they want to use this equation. But yours is not a level field next week, okay? You fire from the table, it lands on the ground. But this one is, you know, kicking of a football. This one lands at that same height. So I'll put this in. This is initial velocity, cosine theta. That would be this. Then I can put my time here. So this would be 2 times initial speed sine theta over g. Rearranging this, I get initial velocity squared over g times 2 cosine theta sine theta. And I only rearranged it because that looks familiar to me. Does it to you? What is that? It's one of the trig identities. Now you may not remember, but where would you find it? Appendix B, good, right? Now, that's why I emphasize that Appendix B. Don't forget all those integral tables, those derivatives, your geometry, and in this case, your trig identities. And this is a double angle one. They're all back there in Appendix B here. And so this is initial velocity squared times the sine of twice the angle. And looking at it, it is helpful that way. Now, back to your question, if the numbers were just given, kicks the football at 60 degrees at a speed of, you could just put in the numbers. You could just put cosine of 60 times sine of 60, and you don't need the trig identity. But this will help me ask your question. Then, if I am actually kicking this football at a particular speed, now, when I say particular speed, because if I kick it harder, I would expect it to go farther, right? Okay, but at a particular speed, what angle do I kick it so it goes its maximum? So I come over here and I kick it. Now, like I said, if I just give it a little kick, it's not going to go very far. I give it a hard kick, it's going to go farther. And you can see that right here. So but for a particular speed, you know, if my fastest speed is 20 meters a second, what angle do I kick it to go the furthest? Answer? Do you see it in here? Yeah, it's going to be 45. I mean, if we look at some of these here, when does that become the biggest? Well, the biggest the sine function ever gets is 1, right? At what angle? Yeah, when 2 theta is 90 degrees. So theta would have to be 45 degrees. So it is the 45 degrees that gives it its maximum distance. And that, which I think was your question. Now I'll even add to that, because that will change. That's without air resistance. Okay, and so when we go a little bit further here into Bernoulli's principle, we'll do a baseball. If you want to hit a home run, it's not 45 degrees. It's going to be about 35 degrees. So you'll use the spin of the ball and the air to change that. But without air friction, if I'm trying to hit a home run, 45 degrees. The ball goes up at 45 degrees. And that's not to say I kick a football at 45 degrees. If you know anything about football, they don't usually kick at 45 degrees. Why? Yeah, this is the longest distance it goes, and you don't necessarily want that, because if you kick it out of the end zone, all they do is pull it back to the 20. It's much better to let them catch it and tackle them, or knock it out of their hand too. But all right, but hit them and get it out, and get them on the 1 yard line or the 2 line. In fact, if you watch the Super Bowl, you saw a great one, the first play the New England had, right? Anybody see that? First play right there on the 4 yard line. They get the ball 1 time, safety. It's like, oh, that was pathetic. Oh, but anyways, that was, and it worked brilliant. Got them back in the end zone. They tackled them back in their own end zone. They had 96 yards to go or something ridiculous thing, and they were way back there. So you don't always want the maximum, but if you're hitting a home run, you do. If you're playing a game of tennis, you don't. What do you want here? And you can kind of see then, back here with the numbers, what if I want it to be in the air for a long time? What do I do? See, and that's more of your punt. It's not so much about how far is it going to go, but what you want is time. You want time for your team to get down there so that when they do catch it, as soon as they catch it, you hit them and hopefully knock the ball out of their hands. You're trying to time it just right. Don't hit them early, don't hit them late, but you need time. And so the angle increases. What would give you the most time? 90 degrees. Of course, that doesn't get the ball downfield, so you don't kick the ball straight up here. But if you had a tennis ball and a tennis racket and you just want it to be in the air for a long time, I mean, hit it straight up. And it's there in the air for a long, long, long time. It doesn't go anywhere. And so you want to balance that. So straight up is a long time. 45 gives you the maximum distance. And so there's some other issues you might want to know too here. Did I see a question? Yeah? Okay. So there's a set of good questions. And in fact, I think we might have asked, oh good, just about all of them. Now, we'll do more projectile motion, and I'll put some numbers in there. Probably not till next week, because let's look at some other cases. I mean, I spent a long time, obviously, today with projectile motion, and you'll see most of the problems in this chapter are projectile motion. They're a good place to start. They're a good place to teach the students about two-dimensional motion. It has constant acceleration, but will all of our problems have constant acceleration? No. And will all of them be projectile motions? No. There are other motions. How about just going in a circle? Let me erase all this and just talk about a circle here for a moment. Moving in a circle is another good set of problems that will be a two-dimensional motion. And let's look at the math and the equations associated with that. And let me use this as an opportunity to use your math that you've learned between now and when I had you in Physics 102. Watch, let me draw a picture here. So here is a circle. So let's say this is the path it's going to take. I'll take an object like a baseball or something and tie it onto a string here. So I've got this baseball and I'm swinging it around, kind of like you've seen the Little League guys, you know, they're practicing. So the coach is spinning it around, the ball comes around, they're all standing in a circle hitting the ball. Okay, so the ball's going in around here. Let me ask you this, is the ball accelerating? I mean, even if you're going around at a constant speed, if this is a car going 45, 45, 45 on an on-ramp, is it accelerating? You sure it is? It's always going 45. Right, but it is changing directions. And what was our definition of acceleration? Change in velocity. And can't velocity be a number and a direction? So is this an acceleration? Yes. And we went through this in 102, so hopefully you haven't forgotten it. Yes, that is definitely an acceleration. But what we couldn't do in 102 is could you calculate the change in velocity, even though its speed doesn't change? We didn't have those tools back in 102. We have them now. How do you calculate a change in direction? Well, you got those little I-hats and directions and the little vectors. So let's do that. Let's calculate the acceleration of this. Now, I'm just going to jog your memory. See if you remember. We called this a centripetal acceleration. We put an A with a sub C. You guys remember that from 102? Okay. And like I said, what is this class about? Well, take the information you learned from 102, take the calculus we learned in 150, let's put it together here. And so in 102, if you remember, we called this a centripetal. So what direction was it?
Towards the center.
Towards the center of the circle. In fact, let me draw a picture that I'm hoping you haven't forgotten. I'll put it over here. We'll take an object, and for some reason I always do baseballs, I guess, because springtime, baseball's coming up here. That's really the only thing I can know how to draw. So you get a little circle, it's real easy, 2 lines there. All right. So draw a little baseball here, but if we look at the baseball in terms of motion, let's say the baseball is moving this way. If you apply an acceleration in the direction it's moving, as opposed to an acceleration in the opposite direction, what happens? How are those different? What would this acceleration do to the ball? Right, it's going to make it go faster. And that was kind of the thing we learned about in the first chapter. Right? Now, what does this one do? Yeah, this one makes it go slower. And maybe you could even see it in the math. If I put an equation, v equals initial velocity plus acceleration times time. If the initial velocity is, say, 10, and your acceleration is, say, 5, as time increases, doesn't this number get bigger and bigger and bigger? And that's what you're saying here. But if the initial is 10, and the acceleration is -5, what does this say? Smaller, smaller, and smaller. Actually, and then tells 0, and then you might say it goes faster in the negative direction. Fair enough? So this is this picture. But wait a minute. Even before we get to this chapter, don't miss this one. What if the object was going that way? And the acceleration is negative. What does that do? Yeah, that still makes it go faster. So the point here in the lesson is, if the acceleration is in the direction it's moving, it will go faster. It just will be more negative. In other words, my initial speed is -10. My acceleration is -5. And as time increases, this whole thing just gets more negative, more negative, more negative, more negative. So it still is faster. It's just faster in a negative direction. So that's why we never want to say negative acceleration means slow down. Does negative acceleration mean slow down? No. Negative acceleration means acceleration is along the negative axis. And if it's already moving along the negative axis, then it's speeding up. So we need to be careful here. So that's why we like to look at these pictures and say, if the acceleration is in the same direction as the velocity, it will go faster. And what if the acceleration is opposite to the direction it's moving? Yeah, it goes slower. And this is chapter 2 mathematics, right? This is the stuff that I didn't draw the picture, but hopefully you'll see it's the same thing we did back in chapter 2, and something we already talked well about in Physics 102. So I think you know all that. What I'm adding to it now is this piece of the puzzle. What direction is the acceleration here? What makes it turn? So if it's moving this way, and acceleration is that way, it goes faster. If the acceleration is that way, it makes it go slower. How do we make it turn? Perpendicular, right? Good. So looks like you guys remember it well here. A acceleration that is perpendicular to the motion will make it turn. It won't make it go faster, won't make it go slower. Now I want to prove that to you. Okay? In a different way than we did in 102. In 102, I spun the ball, pulled on the string, felt the tension, and said, what direction is it? Okay? And then, in fact, I just did that for the 102 yesterday. But for you guys, it should be done mathematically. Shouldn't it go towards the center of the circle? We should be able to apply our math. We should be able to get an acceleration vector that is perpendicular to the velocity vector. And I claim we can if we are careful with our new form of mathematics with the I-hats, the J-hats, the directions, the arrowheads. We can figure this all out. And we will. In fact, we won't even use too much I-hats and J-hats. We'll use more geometry and calculus to solve it there. But that is the point here. And so this acceleration is towards the center of the circle. In fact, in 102, not only do we say it was towards the center of the circle, so we called it centripetal acceleration, I gave you the formula. Anybody remember it? Yeah, good. So it's velocity squared over the radius. So if the ball is moving with some velocity v, going in a circle of radius r, that's what it comes out to be. And if any of you remember from 102, I said, well, when you get to Physics 121, we'll work it out. I will work out the number, that is v squared over r, and I will work out the direction. So here we are. Let's work it out. This is two-dimensional motion, and I should be able to prove that to you now. I should be able to prove that if I take an object going at a constant speed, what direction is it? And what is its value? So let's use the answer to every problem in the chapter to get started. All right, how do I calculate the acceleration? Acceleration is the derivative of the velocity vector, right? Well, let's draw a couple pictures, and I think we'll have time to finish this. Yeah, we'll have time to finish this one, but we'll have to wait for us. The next step, which what if it's going in a circle and changing its speed? But let's just start here. What if it's moving in a circle at a constant speed? All right, now if I were to draw this picture, I might do something like this. At some moment in time, here's the baseball with some initial velocity vector. A little bit later, it's going to be over here with some final velocity vector. Fair enough? And if I take an origin to be right here at the center of the circle, I might call that the initial position and that's the final position. Fair enough? Now let me draw a couple of triangles. And I say that because if I draw the position vector right here, well, this would be initial position. This would be final position. Fair enough? Remember all that good stuff we learned last chapter, the parallelogram? How would we add those two together? Not that we want to add them together, but if I did, what would they look like in a picture? Wouldn't it look like this? And from here to here would be the sum of the two? I want to know the difference. What's the difference between, what's the change in position? What's the delta R, the change in position? Isn't it the other diagonal? Right. And so this is the delta R vector. So keep that little picture in your mind here in this little triangle, because I'm going to draw another little triangle using vectors also. See this initial, see this final? How would I draw those vectors? Well, I guess this would be it. This would be initial velocity vector. This would be final velocity vector. Okay? Now again, if I wanted to add them together, not that I say I'm going to, but if I did, what would I draw here? When I draw a little parallelogram there? And the sum of them would be from here to here? Fine. What's the difference though? Where is the difference between them? And so there's the change in velocity vector. Okay? And so that's why I said part of this little proof will be geometry. I want you to look at this real carefully. Look at these two triangles. I claim that they are similar triangles. Isn't that leg the size of that leg? Isn't this an isosceles triangle? Because this is the radius of a circle. And I also claim, isn't this length the same as that length? Because these are the velocity vectors, and I'm saying it's going around at the same speed. Okay, so that's the same as that. And I'll go you one step further. I claim that that angle there is the same as that angle there. It comes from right here, but if you draw it out, of course, this angle here is then perpendicular here, and likewise this is perpendicular. And so as I trace this back like that, something to that effect, this angle is what I'm looking at right in there. That is theta, because that angle plus this one on the outside have to add to 180, and this one have to add to 180. So they're the same angle. So those are similar triangles, and here's why I care about it. Similar triangle means that if I take this leg, delta r, and divide it by r, and I'm not going to put initial and final anymore because they're the same size. And I'm not even going to do vectors anymore because I'm just going to talk about the size of the triangle. Wouldn't that be the same as delta v over v? And if you see all that geometry, and now with one step of calculus we're done, watch this. What does this really mean here? This means the limit as time goes to 0 of delta v over delta t, right? Let me replace delta v with delta r times v over r. And so this becomes the limit as time goes to 0 of delta r times v over r, and then my delta t is still there. What is the limit as delta r over delta t? What's that right there? Isn't that velocity? So this is velocity times velocity over r. It's v squared over r. Yay, there we go. Okay. So there's the proof. Little geometry, little similar triangles, a little definition of what is the derivative, and the magnitude is v squared over r. Now that's the magnitude. What about direction? Well, I'm hoping you see that in the picture too. In the limit as time goes to 0, doesn't this angle get closer together? And as this gets closer together, actually it doesn't even matter if it gets closer together, but what direction is delta v? Isn't delta v down towards the center of the circle? And so there's our direction, towards the center of the circle. And so I have the two pieces that I wanted to show you. If something is moving in a circle at a constant speed, does it have an acceleration? Yes. What direction is it? Towards the center of the circle. What is its magnitude? How do you calculate it? V squared over r. Okay? A little bit of work. But we're going to use that a lot. Well, we'll stop there and say, well, okay, we're good for this week. Encourage you again. Finish up chapter 3 if you can and start working in 4 as much as you can. It'd be great if you did a lot in chapter 4 this weekend, because when we come back on Monday, I'm going to be doing some real concrete examples for you. And I bet you will learn a lot more if you've gotten to a place where you're stuck after you've worked on them this weekend.